I may have to leave early at 5:30.
What have you learned?
So the difference between like the Lagrangian and Hamiltonian is like Lagrangian works on like the TQ space, on the like the tangent space, while Hamiltonians work in cotangent space. So make sure I had all that notation or vocabulary again.
Yeah.
And now we're starting to see like actual physical things like action and
Hey,
energy defined.
What was the last thing?
There are like actual physical things defined now, like action and energy.
Well,
it gave a kind of funny.
Well, okay, energy is the same, right? It's the same as the Hamiltonian.
Pretty much, yeah.
Numerically,
yeah.
It's just expressed in different variables. Action, I wouldn't call action a physical quantity. Right? And action is not even uniquely defined. There's some. There's some gauge freedom there. Kind of.
I can only hear you. I don't see anything.
Okay, is this off? Uh-huh. Yeah. Yeah, so the one important thing is that it doesn't work for any symplectic manifold, right? It has to be T star Q and TQ. Like if you have an arbitrary symplectic manifold which is not a rotation bundle, then there's no Lagrangian theory for it. At least globally. So for example, last time I gave, or 2 weeks ago, I gave an example of a particle in a magnetic field, which in the plane, for example, you could write a symplectic form like this, just the area form on the plane, right? And you could consider x dot and y dot, write them out from here, and you will see x dot equals, again, the sign might be wrong, but something like that, right? So this is a rotation in a circle. So like you can model a magnetic field, a charged particle in a magnetic field by this symplectic form, which does not have the form of dq/dp, right? Of course, you could say that let x be my coordinate and y be the conjugate momentum, but that doesn't make a lot of sense in terms of the symmetry of the problem, right? Why would you? It's an arbitrary coordinate system, so it seems strange to split them that way. And this gets much worse on the general manifold. Like if you put it on a sphere and you have a monopole in the center of the sphere, you have a constant magnetic field pointing outwards. And the symplectic form is going to be, again, the area form on the sphere, with dr, I should use phi, right? No, I should use theta. And in this case, it's not even clear what I should call momentum and coordinate, because these things are not defined globally. Like theta is not defined globally. Not dr defined, right? because they don't fire not defined globally. So it's impossible even to interpret that as a coordinate and momentum. So a Lagrangian theory for this wouldn't exist. But if I have dp/dq, then I can do Legendre transform. And one more important concept that comes up in that process is of a differential equation, right? So what's a differential equation?
Trick question. Wait, in the normal sense or in the differential geometry sense?
Different geometry
I had trouble following that point.
So let's think about this. So we've seen first order differential equations on manifolds already, right? Like x dot. When we defined integral curves of vector fields, right? The equation was x at the point of the curve is equal to the derivative of the curve, right? So this is why vector fields can also be called differential equations, or ODEs, which are linear, not linear, just first order. Okay. But what about ODEs of second order, for example? Like what geometric object corresponds to the second order differential equation?
Separate into two.
Okay. And what are those parts? So geometric.
That's the Hamiltonian, or the Lagrangian.
I'm just giving you. It's just an abstract thing.
So you'll need something in the same way that like the vector field kind of acts like a time derivative. You'll need something like to act on the vector field as another time derivative. So you need shoot, what's
If this is velocity, we need an acceleration, right? If velocity is an element of the tangent level, then the acceleration is an element of what?
Oh, wait, we
So
just
think
need the derivative, covariant derivative to the vector one.
What covariant? There's not covariant.
is that the fiber derivative? Or, I'm just throwing words out. I don't know.
No, if the vector field is the time derivative of the curve, then the acceleration will be obviously the time derivative of this vector field, but as an object of, as a geometric object, but an element of what bundle?
The cotangent bundle?
Every derivative on any manifold, right, puts you into the tangent bundle of that manifold. So if C of t is on M, C dot of t is on Tm, and then C dot dot, which is dot of C dot, right, is in Ttm. But is this not obvious? I mean, you have a vector field. A vector field consists of a point. It has two parts. It has the point to which it's attached, and it has the vector part. So vector sitting at that. Okay. And then you take a dot of this, like in local coordinates, you would get 4 parts, right? The first 2 parts would be the same. They just denote the point to which this thing is attached.
Sure.
This thing will be attached.
Exactly.
And then the other 2 parts will be the derivatives of these 2 bits. C dot and then V dot.
Okay. I guess my first thought So my first thought for acceleration was always like, never mind.
Like in physics textbooks, you see this derivation of the acceleration in like polar coordinates, for example.
Sure.
And it's complete bullshit. Like it doesn't make any sense from a differential geometry point of view. Because the only way to make that derivation is to assume that your manifold is Rn, and to use the fact that the basis vector fields, like you like to call them r hat and beta hat, they are expressed in a certain way with some components through x hat and y hat, and this is some combination of x hat and y hat. And these guys don't change. Like the time derivative of this is always 0. Like they are constant. That's what you assume, right? But on a general manifold, a constant vector field doesn't. The word constant doesn't have a meaning, right?
Well, I mean, so the way I think about it, right, is if you think like acceleration is something that you're in humanities, I'm just going to be using relativity terminology, so I think we're talking different things. But like the thing I guess that I was thinking about is like acceleration is like an observed dependent quantity, right? And it's just you take the four velocity of that observer. That's what it counts as a time coordinate. And then let's just say this four velocity is c, the acceleration would be the like nabla c of c, right? And then those extra terms come in as Christoffel symbols, right? So if you're in like a polar like coordinate system, all those extra acceleration terms come in with the Christoffel symbols. Because acceleration is necessarily, well, I guess here it doesn't matter because we're in classical mechanics and time is still parameter. Because from a space-time perspective, acceleration is not necessarily stick with field, it's observed dependent.
There is no uniquely defined time. I mean, here the time parameterization is part of the definition of the curve, right?
Right.
And in general relativity, when you have a world line, there is no parameter on it. I mean, we introduce a natural parameter using the metric, which is the proper time, but it doesn't exist a priori. But obviously, you can introduce additional structure to identify elements of the second tangent bundle with elements of the first tangent bundle, and then say that acceleration vectors are actually vectors and not this. But it's additional structure. Right? Like here, it's pretty strange in Rn. You have to use the fact that it's Rn and assume that x hat and y hat are constant, which is weird. That you have to refer in this derivation. You have to refer to this very specific coordinate system. Right. Doesn't make a lot of sense.
Wait, in that case, I kind of follow-up question. Is there a way to like make your definition of acceleration compatible with mine? Because at least on the level of the tangent model, right, my definition of velocity is the same as yours.
Well, the velocity is obviously the same, but how do you define the acceleration again?
So the acceleration is like
That's the covariant derivative of the velocity along the curve, right?
Yeah.
So like velocity is d by d tau of point, and acceleration okay. Why are you claiming that the acceleration is a vector?
okay, so here's an example, right? So I create a box, right? And in this box, you put like let's say a rock. You connect the rock with a spring to the fixed box, right? And so whichever, so the opposite direction of where the rock is moving relative to the center is what I call the deceleration, right? So instead of free falling zero acceleration, if I'm standing on the ground, the rock will be going down to measure the force of that. And I'm telling just tell me that I'm accelerating 9.8 meters per second up to the floor is, right? And so that way it has a clearly defined spatial direction for me as an observer.
No, but in VR, that's frame dependent. Right?
No, exactly. That's what I'm saying. So I guess it just like it's
No, but
necessarily
picking a
different
frame lets you identify objects of different.
Yeah. So yeah.
levels
So
of
my
this
question
thing.
is like how would I from that recover my like frame dependence? Like I'm thinking like what is the identification?
Jacobian, whatever the derivative, whatever the Atlas map. I mean, we know that on the higher levels of the tangent bundles, the Atlas maps are just one more Jacobian matrix, like one more derivative of the initial mapping, right? So like one more.
I think it's
Right. I mean,
I think literally
it's just like in a RAN in usual coordinates, you can identify accelerations and velocities. No problem.
yeah. No, I think what's happening right is you're like take my definition of acceleration, take a random observer, but in classical mechanics you have global initial coordinates, so every observer is the same. And once to have like a notion of spatial, that's where you're going. Because at that point, right, you're thinking of things as like an acceleration needs to come through back to an initial value, which is a point in the tangent bundle, right? And then the tangent bundle of that will have the dynamics of the system that it would see dot. So never mind. This is like a nominal issue.
I mean, there's also some mixing because a covariant derivative turns vector fields into vector fields, right? It doesn't really, it preserves the bundle that it acts on.
Right, which is
So
the
it's a little
reason
different.
why I was initially a little baffled with these
It's a little, it's a different derivative.
I think what's happening is you take my formalism, you make like you pick an observer, you do a spatial slicing, and then you can do classical mechanics, and that's where your formalism comes in. If you're doing geometry on geometry.
This doesn't have anything to do with time slicing. T is just an arbitrary boundary. Proper time will boundary everything.
But to do classical mechanics requires a set.
But this is a completely generic differential geometric. I'm not assuming any additional structure. Right. So it's a question of what is your covariant derivative? Because
So I mean,
it's
like,
not the same as just a literal derivative along the boundary of the curve. Right?
yeah. But I guess what I need to say is like
Covariant derivative, you take parallel transports, you parallel transport stuff along the same curve back to the initial point, and in the fibril above the initial point, you take the derivative in that vector space, which is why the resulting element is an element of the same vector space. Whereas here, just the normal d by dt doesn't assume any connection on the bundle, right? Which means that you're basically trying to compare two vectors at different points of the curve, which, as we know, doesn't make sense, right? Which is why you have to raise this to a new tangent bundle.
you also might
Be able to talk
be
about
political
this.
about to say.
But
But one should interpret determining mechanics as having a first dimension. Insofar as like Newton's first law, like an object upon which no force is acting is a straight line. So a straight line defines a connection, right? A straight line defines an outer parallel. So in a sense, you play the mechanics. Because like the thing is, right, whenever you do physics, that's boundary is necessarily going to be, be important.
but well, Newtonian mechanics doesn't contradict Lorentz
I'm not saying
transformation. You can derive Lorentz transformation from Newtonian.
was this part of your axiomatization. Wait, why does it? Oh, like Newton's three laws don't contradict it, or like classical mechanics, and like there is.
Just the first law. I mean, the second law needs to be rewritten as enough, but the second law involves.
Oh, you can get all three of Newton's laws from Einstein.
But that's the opposite direction. I'm saying Lorentz transformations do not contradict Newtonian mechanics. As in the first Newton's law, isotropy of space.
No, sure. Like special relativity is all about the virtual things. Because there should be no reason why they contradict each other.
But yet usually special relativity is formulated. Like one of the postulates in the formulation is the constancy of the speed of light, which should not be. The possibility of the existence of a speed which is constant in all Lorentz frames is already encoded in Newton's law. In fact, there's one more free parameter which is allowed in Newton's laws, which is the Hubble constant, which allows for a time varying speed of light. Yeah, it is. Not the Hubble constant thing. That's a derivation by Fock in 1910, St. Petersburg. What's a differential equation then? Well, if we just look at a derivative of this kind of a vector field, then you notice that there's some redundancy in this description. Specifically, that C dot already equals
I was about to ask, like, why you need 4 bits of information.
right. You need 4 bits of information just because that's how the tangent of a bundle, the tangent of a manifold is defined. It always doubles the amount of information. But yeah. So in the tangent bundle, let me say this. So a curve in a tangent bundle, what does it look like? Not a curve in M, a curve in Tm, right? What does it consist of? So it projects obviously to a curve on M, and then you have a vector above that curve, right?
It's kind of like a curve in space, I guess.
Right. So it's a curve in M plus kind of x of t in t, c of t, right? And by plus I mean what? Yeah.
Like plus you mean more like set unit, right?
Okay. Yeah. So when is this a differential equation and not just a curve in Tm?
When ECT is CT dot.
Yeah. So this is called an ODE, first order ODE, if and only if x is equal to c dot. Right? So we can do the same to curves, second order differential equations. So the curve in TTM consists of a lot of things, right? It's c of t, it's x of t, x of, maybe I should write c of t, right? And it doesn't matter. And then, what else? So the third part will be an element of, well, it's something arbitrary, right? y of t. Okay. And it's a ODE, second order ODE. If what?
X equals c dot y equals x, y equals x dot.
Right. So x equals y equals c dot, and z
Equals x dot equals y dot.
right. Okay. Which is, as you said, that's what you meant, right? So you can break down the second order differential equation to two first order differential equations, by introducing a new variable, which is this middle part.
Why do you have an x and a y? What are x and y?
Because the double tangent bundle contains 4 pieces of information, right?
Oh.
And the middle two are usually the same for actual curves. So this is the differential geometric definition of the differential equation.
Does this handle, let's see, does this handle nonlinearities?
Linearity doesn't even make sense on the manifold. Linear in what? The unknown here is C of t, right? But it's a point on the manifold. What does it mean to be linear in the point of the manifold? Right? In fact, finding a coordinate system in which this equation becomes linear is basically solving that equation. Right? It's just straightening out the vector fields. So it's just as good as solving the equation. Because linear equations you can always solve. Right?
Okay, I buy this.
So yeah, this is the most generic there is. And obviously you can continue this with high order of these results. Okay. So if you were confused about this, you can try and read this again with this new knowledge, or you can just read Arnold or something for the traditional derivation of Euler-Lagrange equation. Right? Only I think he does this in the opposite direction, which is why I decided to stick to this book, because it does Hamiltonian mechanics first and then passes to Lagrangians. But most other books go from Lagrange. I guess that's the historical way of thinking.
People, like, so books that do Hamiltonian and Lagrangian every time that's usually the perspective that comes with.
Not necessarily. No. It's mostly because the Lagrangian theory can be derived from physical principles. D'Alembert's principle, right? It gives you Newton's equations are second order, so it's most natural to derive the Lagrangian theory from that. But then, if you want to do a different geometric approach, then Hamiltonian theory is generally more geometric. Okay. Anyway. Oh. Any other questions about Lagrangians? So obviously, the simplest example, which we can try. Compute. If my Hamiltonian is just p squared over 2m, where by this I mean symmetric, right? Then what's my Lagrangian? Right. So first of all, what is my fiber derivative? Velocity is the fiber derivative, right?
So, G, I, J, P, I.
Yeah, so in local coordinates, the fiber derivative is just literally the derivative with respect to the variable in fiber, which is p. So it's just d by d I of right? Which is I.
Do you lose a factor of m since Pij is factor 2
factor.
Pij is down here?
Okay.
Or symmetric.
It's a quadratic form. Yeah. So the Lagrangian is PQ dot, i.e. PV but what is the PV thing? So it doesn't make sense to multiply the elements of PV. Well, okay. So like P of V, right?
Yeah.
Minus H. But then there's a problem with H too, right? It's a function on T star Q. But L is supposed to be a function on GQ. So this is L of basically V. Right? This is fine. This is already a function of V. P acting on V. P is a function on T. So that's fine. What about H? We need to re-express P in terms of V, right? So we just need to basically pull back H by fiber derivative, right? Because the fiber derivative, let's say, of a Lagrangian is a mapping from TQ to T star. And backwards, fiber derivative of Hamiltonian is backwards. So this is just going to be H of fiber derivative of H inverse V. Right? That's it basically. So we know that P, again, in local coordinates, P equals M, well, okay, MVI, but with a lowered index, right?
Sure.
So MVI, right? And then P of V equals obviously M squared, right? And then H of P equals MVMD, so right, subtract the 2. obviously it's not different from the flat metric, but it's useful to know it works. If you quantize this Lagrangian, you don't get the Laplace operator. That's interesting. It's Laplace plus curvature.
Really? Is it too out of the way of this course to quickly explain that?
Yes. All right.
Wait, Alex, one last question though. Is this explaining my answer?
Yeah.
Alright, cool. That's my reading
Okay, and then the next section was about the Legendre form, which we know is the fiber derivative, right? But again, it's about the question of when is there a Lagrangian theory for a Hamiltonian theory, and when is there a Hamiltonian theory for a Lagrangian theory, right? So you might have heard that in quantum field theory, for example, you usually use Lagrangians for some reason, and it's not completely clear why. Like in classical mechanics, Hamiltonians seem a lot more symmetric and nice, geometric, etc. Right? In quantum mechanics, we use Hamiltonians all the time, and almost never mention Lagrangians. And then in quantum field theory, for some reason, we forget about Hamiltonians altogether, and it's just like, so why is that? Right, so what's the property of Lagrangians which makes it difficult?
Oh, it's very symmetry. I could read you some two
It's not hyperregular. That's the word.
What the hell is that mean?
It means that the matrix of the second derivatives with respect to velocity is not exact. So it's impossible to solve this equation for E. Like this matrix would be non-invertible, for example. Okay. So if you consider a gauge theory with a massless particle, then Lagrangian contains a term which is like A times B. And it's linear in B. So the matrix of second derivatives is going to be 0 with respect to B. Right? So it's impossible, like the canonical momentum doesn't exist if it's a massless particle.
Oh.
And
are the fake momenta like that you create in the
yeah. So that's called a constrained Hamiltonian system. Right? So we know how to deal with constraints in Lagrangian theory with Lagrange multipliers and all that stuff.
Wait, I should think about like trying to solve it in a game where like deviate.
What?
Why is this? You mean like you? Wait.
It's a constrained system because what seemed, what was supposed to be a second order differential equation turns out to be a first order differential equation, etc.
Oh, wait, are you saying that term is what gives
I think.
symmetry? That
What?
Yeah.
No, I'm saying with massless particles, like you can consider Lagrangians, which may be approximations of hyperregular Lagrangians, but are more convenient to consider for physical reasons, like this of a massless particle, right? In a particle in strong magnetic field or something, okay. Where you just forget about the mass term, and then.
Oh, you're saying the particle velocity v is faster?
Yeah.
Oh, I think you're talking about your electromagnetic field.
Oh.
No,
This
the problem
particle.
there is that you have to solve like you either impose like deviating zero before or after, and that's what you want to do with that.
That's other.
Okay, sorry,
Uh,
I'll use that one.
Yeah, so you can open the Wikipedia article for constrained Hamiltonian systems, and there's a good example there with this type of thing. You consider a massless electron in a vector potential, and the Hamiltonian is undefined, so you want to develop a theory of constrained Hamiltonian systems. Okay. And it's surprising, but the first person to do that was Dirac. Right? And his method involves extending or generalizing the definition of Poisson brackets. So you take the usual Poisson brackets, and you find that they are degenerate in some sense in this case, because
Oh, this is the thing when you say this is on back to algebraic.
if you take Poisson brackets in canonical coordinates, right, like Qi, P, and you make a matrix out of all the pairwise Poisson brackets like this, you get the matrix of the inverse matrix of the symplectic form, okay, by definition of Poisson brackets. So if too many of the Poisson brackets are 0 or something like that, then the symplectic form doesn't exist. That's basically the problem there, right? So you want to change the Poisson brackets somehow to make this matrix invertible without breaking the equations of motion. And so Dirac found a procedure that allows you to account for all the constraints and add some extra terms to the brackets to get new brackets that are called the Dirac brackets. They allow you to define Hamiltonian systems. So for example, but what's interesting is that as a result, for example, for this case of a particle in a strong magnetic field, which is massless, you will get non-commuting coordinates in the non-commuting coordinates. Like x and y will not commute anymore. Just like in that example with dx, dy, dx, dy, which you could also call non-commutative geometry or something. But it comes up naturally when you have a degenerate system, or constraint system. And if you're interested, I can give you a reference for a different geometric version of this, which is actually much easier to understand than Dirac's procedure. Dirac's procedure is described like in Wikipedia, I think, and in Weinberg or something. Usually, it's described only in quantum field theoretic contexts, and it's really confusing. Dirac's procedure. So you take these brackets, and then you take you have a bunch of constraint functions, which are functions of q's and p's, and they equal 0. That's your constraint surface, and you include brackets of like everything with the constraint functions and constraint functions between themselves, and then these brackets will be equal to some other functions which have to be included in the same list, and like it's an iterative procedure until you start getting back the same function you started with. It's not completely clear why this procedure works and why it makes sense.
It seems.
Whereas in the differential geometric language, all of this is literally you just take the Poisson structure on the initial manifold that you had, and you restrict it to a submanifold. And you get the Dirac brackets just like that. Requires a little bit of proof, but it's much more natural. But anyway, I mean, it's not. It's not trivial, and this which is why it's not taught in undergraduate classes. Even in quantitative classes, I've never seen this. Although it seems like a very natural problem, right? We've done constraint systems in Lagrangians. Why not do them in Hamiltonian?
That's because they started doing Hamiltonian mechanics.
Oh, the ninth week, yeah. just now I saw at Gotham's desk I saw a copy of the 2009 exam in 185.
Yeah.
And the first two problems involved like writing down the Lagrangian in the equation of motion, and the other three problems didn't involve neither Lagrangians nor Hamiltonians. Just rotational bullshit.
I think my final was one problem on Lagrangians, one problem on rotation, and one problem.
Yeah. Okay, so if a hyper-regular Lagrangian or Hamiltonian, the opposite way, is a Lagrangian for which this equation can be solved. The equation for the Lagrangian for which the inverse of the fiber derivative exists, right? Or the inverse of fiber derivative of the Hamiltonian exists. That's when it's hyper-regular. Does that make sense?
So I think I was on calculation. And if I see that,
I think Arnold also uses the word hyper-regular.
no fiber.
Well, yeah. But in all classical mechanics books, you will see this assumption that dl by dv I dvj is not zero determinant. This is a necessary assumption to be able to at least locally solve the equation. So it expresses the equation. So we have here's this example. We have the definition of canonical momentum, right? In multiple coordinates, it's like that, right? But to write down Hamiltonian, you need to invert this. This is a function of v, right? You need to invert this and write v as a function of p. Which is not always possible. It's only possible if the matrix of second derivatives of that is not determined. Okay. Right.
I. There's like the inverse of the theory that you're talking.
Yes, the inverse.
Yes. But it's local.
Well, yeah, I mean, if you want to invert this globally, you have to assume that the determinant is not there everywhere. Still, even in that case, the inverse mapping theorem doesn't guarantee global invertibility, but it's more of a coordinate problem than a symmetric problem. So, okay. But if your Lagrangian Hamiltonian satisfies this property of hyperregularity, then you can invert the fiber derivatives, right? And these guys will be isomorphisms between T, Q, and T star Q. And in that case, like your theory is completely equivalently defined in both forms, right? And you can just read it between both of them. But in quantum field theory, where there's a lot of gauge symmetries and other stuff, it's usually people use logarithms. Plus you have Feynman half integral, which is in terms of the logarithm theory.
What's the opinion of the half integral?
I mean, it's an object which doesn't exist. So it's a physical instrument to derive results before proving them.
Do you believe in that?
I mean, that's what every physicist believes. It's an inexistent object, right? Which has certain patterns to it that allow you to derive object and derive proposed equations. It's not
The
defined, right?
matter doesn't exist. It's not because it doesn't exist. It's not
I mean, it doesn't have a physical meaning and it doesn't
Measure
exist.
of impermanence.
It has a physical meaning somewhat. Like you could say what it's supposed to be.
So you approximate it by, let's say, infinite sums of Feynman diagrams, which don't converge. That's not a problem. But they don't converge because the integral doesn't exist. And the Feynman diagrams are the physical objects.
Yeah.
Okay. So the integral itself is defined as this series of Feynman diagrams.
Yes, yes.
And so the goal of quantum field theory is not to compute the integrals, to compute the Feynman diagrams.
Yes.
But then what they mean is a physical question, right? And that physical question is explained by this analogy with the path integral and the analogy with classical mechanics and quantum mechanics of probability, of transition probabilities and stuff. So it's a very interesting physical instrument, which should not be taken as a derivation of anything. And I don't think anyone believes that it can be fixed in any foreseeable future. Like, the only possibility for it to be fixed is if everything fundamentally is discrete and all theories should be actually lattice theories. And somehow the partition functions in them converge nicely, which is also highly improbable. Like, there's basically only one theory in existence, lattice theory, which people have been able to compute the partition function of, which is the 2D Ising model. And that's it.
Well, that's
Is
the
that
other way that
very
they try to
promising?
quantize gauge theory, right? They define it on a lattice and then
Yeah. One problem is that the result depends drastically on the shape of the lattice. Right, so like with continuum limit doesn't make sense. If you want a continuum limit to exist, then it probably should not depend on the shape of the lattice that you choose, right? But it does. Anyway. So in terms of the hyper-irregular stuff, there's not much to talk about. Laurent is taking deep breaths, sighs. Okay, so in my handwritten notes, I have a little bit about Dirac's theory of constraints, which was copied from. It's a mix of that Wikipedia article and some other guy's notes. Just pretty confusing. You can try to read up on that yourself. It's kind of interesting, but it's mostly interesting because of the quantum mechanical application. Okay. And then next week, I should decide what to do. Strictly speaking, there's the topic of time-dependent systems, which is covered in the book, but it's not pretty. It's basically the same. I mean, the only real change you need to make is you replace you replace omega with omega tilde, which is omega minus HDT. And in the Lagrangian analog, nothing changes. In the Lagrangian theory, there's nothing but the Lagrangian. Right? In the Hamiltonian Hamiltonian theory, you have a Hamiltonian and a symplectic form. In a Lagrangian theory, you have only a Lagrangian. Because the symplectic form is kind of, you already live on TQ. So there's some more strict underlying structure in general. But,
So is this structure that
so
was
that's not
also-
really exciting. What?
When you say that you have more structure, but there isn't TQ, then you
Like it's a vector bundle, right? You already have the fibers.
do. Oh, okay.
So like the Lagrangian is a separate function kind of the base point and the fiber point, right? Fiber element. Whereas Hamiltonian is just a function on that fold.
I see.
And there's no separation into P and Q. And omega provides you the separation into P and Q by the Darboux canonical form, right? At least
Okay.
locally.
That's what you're saying.
Right.
Whereas, like, okay, so if we were on a phase space that was already codependent bundle, we get a symplectic form for is D with theta. Whereas in our case symplectic method, we have to specify omega.
Yeah.
Okay.
Yeah. So if I skip this, then there's only basically Jacobi theory left to classical mechanics in the traditional form, right? Have you ever seen Jacobi theory before? Hamilton Jacobi theory. You haven't seen Hamilton Jacobi?
I think it's
You haven't
where-
read about it?
I think it's where Schrodinger derived the Schrodinger equation.
Yes. Yes, no.
Everything Jacobi theory is like that one thing that was in my Haskell was like never enough motivation.
It's probably the most important formulation of classical mechanics out of all. There are three, right? Lagrange, Hamilton, and Hamilton Jacobi.
I know very vaguely what it is, but I've never really studied it.
And it's and it's also fundamentally analogous to optics in a way. So it describes classical mechanics basically as propagation of certain wave fronts in the phase space. And in optics, Hamilton Jacobi equation also exists. It's called the Aiken-Hall equation. Have you ever seen that?
When would we have learned optics nowadays?
That's a good question. One before the maybe.
You think it was taught that one very
Okay, I showed people Aiken-Hall equation.
I was also never in the equation.
Yeah. But you have the wave equation, right? Which is d t squared. What am I differentiating?
Whatever.
Potential. Yeah. Any whatever. Potential vector, potential electric field. They all satisfy the same way.
Yeah.
Minus Laplace. Okay. And then I take Fourier. Fourier in this, in x. Okay. And I get dt squared u plus k squared u.
Now we flash back to distributions.
Yeah.
Fuck that.
And now, so this is called Helmholtz equation. Oh, I'm sorry. Right. Not an x, in t. Right. Okay. This is called Helmholtz. And then you take the geometric optics limit. What's the limit of geometric optics? This is
Goes
wave
to
optics.
infinity.
Huh?
Infinite distance. Or
Infinite,
Tiny wavelets.
infinite frequency, right?
Oh,
Yeah. So you send omega to infinity. I mean, there's no omega. But yeah, you send k to what? Infinity, right? feet infinity. So you have a large parameter equation, and you assume an ansatz for the solution of the equation, right? And we expect the ansatz to be something like some amplitude, which is slow in x, okay, times e to the I phase of x.
Oh, we do that.
Yeah, which is fast. So in particular, it's going to be proportional to omega, approximately proportional. And you plug this into here, okay, and you select the leading order terms in omega or k, okay, the k squared terms, and the equation that you get is nabla phi absolute value squared equals n squared. This is the refraction index. And this is called the Eikenall equation. And it's also the Hamilton-Jacobi equation for optics. Because nabla phi is the momentum, and this is and the action, or the Hamilton principal function, which is called in classical mechanics, is just the Eikenall, which is the, what is it called? Optical length path.
Optical path distance.
Path distance. Right. Yeah. That phrase doesn't make sense to me.
Any
Path.
optics balance.
Right. Whatever. So Eikenall, and it's NDT, right?
Oh, yeah, sure.
Which is also equal to T tau.
Yeah.
And the trajectories of this action are described as the same. Yeah, and in quantum mechanics, you can take the Schrödinger equation and take the high energy limit there, which is the same limit as here. And as the first order equation, you get the same Eikenall equation. But phi here is replaced with the phase of the wave function. And this is the amplitude of the wave function. As you can see, the leading order equation doesn't give you any information about the amplitude because it's slow. But next order equations, and it's an infinite series of equations, obviously, and they're called transport equations. Like, if you know the phase, they allow you to approximately find the amplitude later. That's geometric optics.
When did you learn optics?
What?
When did you learn optics? Like in what context?
In my semester course in optics, maybe?
What semester course in optics?
Yes.
Wait, what were the
Which I think should exist here too.
What were the courses you took again?
When?
Like, what is it? Wait, when's your master's or
Undergrad. Undergrad. First year, first semester is mechanics. Second semester, classical mechanics MSR, like that. Then second semester is thermodynamics. Third semester, so that second year, is electricity and magnetism. Fourth semester is optics. In parallel with that, we have during the second year we have a year-long course in theoretical mechanics. So that's all we're learning how to do. And then third year is a year-long course in quantum mechanics. And on top of that, I don't remember the first semester. The second semester involves statistical mechanics. And fourth year, first semester is also statistical mechanics. So statistical mechanics is also 4 year.
Oh, do you like particles and fields?
No.
Really?
No fields. There was some kinetic theory.
That's the one kinetic theory. Danson just kind of waved his hands and said the word hierarchy a couple times.
Huh. Yeah, so that's it.
So you had one of those semester
Oh, right. So third year, first semester was electrodynamics with all the covariant formulation. Lunch.
I think the only optics here just gets dominated a little bit with second order electrodynamics.
Mm.
227. There's a little bit of it.
Oh, he
Right.
runs Snell's one stuff. I don't know.
See you, Aileron.
Alright, bye.